So just checking in, Josh, you're looking at my PowerPoint, right?
Yep, that's perfect.
Okay, with all the screens going, I like to double check. Welcome everybody. I teach at Coconino Community College, and so those of you who have been to the Festival of Science before knows that we love to participate with this project. We do the science in the park normally, and we have a big open house on Friday nights. And so like a lot of you, we were disappointed we couldn't do the same thing this year, but we still wanted to participate, and we still wanted to have something that families could do, like our science open house. And I had some friends at the college help me with this as we put it together, because everybody wanted to be involved as well. So here's where we're going to head off to. So keeping with our theme of superpowers, we're going to talk about the superpower of lakes. And not just for having fun and cooling off in the summer, but lakes are really good keepers of history. They record what's going on around them for a long, long time. So we're going to delve into how geologists figure that out. And hopefully some folks saw that we had some supplies we wanted you to get. And if you had a chance to get those together, we'll be using them. If you didn't, you can do it after this is over. So the record that we're talking about when we're looking at our lakes is the sediment that accumulates in the bottom. And sometimes we don't think about this. It's kind of one of those out of sight, out of mind things. And if you've ever gone swimming at the beach, let me just go back one screen. We often have nice sandy beaches, and if you were to wade into the water, you might find that things get a little finer grained. So it's very sandy here, and if you walked in deeper and deeper, you get to a point where I think the technical term is icky between your toes, and so there's some really fine grained material, and that's usually when you start swimming. So off here in the deeper parts of the lake, we often expect to see really fine grained material settling out. But it's a little more nuanced than that. And so we're going to investigate what happens with the seasons. We get a real big change in seasons in our lakes, especially in our northern lakes, Montana, the Great Lakes, New York, Alaska, Canada, places that freeze over in the wintertime. Okay, so we think about our seasons. If we had a lake, say in Montana, we would have in the spring, all the snow is melting and we have a lot of runoff and the stream is flowing quickly. So it's got a lot of energy. So it's picking up a lot of the sediment, doing erosion. And we get some fast, cold water with a lot of sediment mixed up in it. And so all that energy brings a real pulse of sediment out into the lake in late spring. And then we might go into the summertime and have our stormy season with winds and thunderstorms. And so again, lots of waves, lots of energy. And so if our waves are bigger, they can erode more sand off the beaches and wash it offshore. So the spring and the summer, we often get a little bigger grain sizes washed offshore, maybe things like sand. And as we go into the fall, our streams quiet down a bit because there's no snow left to melt and we're starting to cool off a little bit. And so things are settling down, wave energy is dying down a little bit. So maybe some things are more like a silt grain size, a little smaller than sand, has a chance to settle down into the bottom of the lake. And if we freeze over the lake in the wintertime, and maybe some of you have been ice fishing and walked out on the ice, and if you ever had a chance to do that, especially when the ice is clear, it's very uncomfortable because we're not used to seeing the bottom of a lake. Usually it's cloudy. And so sometimes you could be ice skating and look down, and 10, 20 feet down, you can actually see the bottom. So that tells us two things. One, thankfully the ice is thick, we can stand on it. But also since the water's clear, that means all the real fine sediment has settled to the bottom. And so we get kind of sandy layers that represent our spring into summer, and then we get a silty layer in the fall, and then we get really fine grain, kind of muds and fine grain organic material going into the frozen time in the winter. And so what we see is, maybe some of you have counted tree rings before, the annual layer of a tree. A lot of our lakes also have annual layers, and geologists call these varves. And so they've got this kind of triplet of sediments that we've been talking about, that we've got a sandy layer that's our spring and summer, and a more silty, finer grain layer in the fall. And then in the winter is when the tiniest things settle to the bottom. Things like mud and all the bits of organic debris and things like that. And that's why the water is often so clear underneath the ice. So how do geologists do this and climate scientists? Depends on the size of the lake and how big of a core you want. So I've seen folks do it with a couple inflatable rafts and some wood to keep stable, and a couple people that can lean really heavy on things. So we could push down on a tube of metal and pull out a core. If we want to do things a little bigger, we can maybe wait till the winter when the lake freezes over, and then we might actually be able to get a drill rig out onto there and drill deeper and deeper down. Or if we're even on a lake like the Great Lakes or Lake Baikal, we might even be able to bring a ship in that can do some coring of the floor of the lake, just like we might core the ocean floor with these big ships. So how are we going to model this at home? Because we want to do some science and I can't bring you on campus, so we'll have to do it with your supplies at home. Well, we're going to try and duplicate those 3 grain sizes. So we got our sand and our silt and then our mud and organics. And if you go to your pantry, we've got some sand-sized grains. We call it sugar and salt. So sugar and salt would work great for sand. And the smaller grains than that, flour and baking powder, things like that would be good analogies. And then if we want the real fine grain material and the organics to kind of give it a little darker color to it, I think cocoa works pretty well as an analogy. If you've ever spilled cocoa, it's incredibly fine grained stuff to clean up. So I think that'll work really well as we try and do our models. And then we need a core, if you will, or a tube that we can see through. So a mason jar would work pretty well, and then we can build our layers inside of our mason jar. So we got a supply list, and again, it was in the announcement about the program that went out earlier. So if you have your supplies, great. If not, you can look at the screen and write down what you need to do it after we do our presentation today. So supply list, 1 quart mason jar. The wider the mouth, the better, because we're going to be trying to drop things into it with a spoon. Something to clean up, although if we do it right, we don't spill, but hey, we got to be careful here. So placemat or a plate or a big cutting board to catch the mistakes. Regular old spoon that you might use to stir your coffee or tea will be fine. And then we're going to need 3 containers, bowls or bags or something like that. So in our bag of sand, we're going to put 1 2/3 cup of our sugar and a 1/4 teaspoon of salt. Want to mix a little bit here. Most of our sand is usually quartz and things like that, but to kind of be close to reality, we might find other minerals and bits of rocks in there. So this gives us a little variety so we can get closer to modeling nature. Then we need our silt, and so we get some flour and some baking powder. And again, a little bit of both kind of gets closer to reality that these could be made of different materials. Silt is just the grain size to geologists, it's not a composition. And then we got our mud and organics, so grab some baking cocoa. So again, we really want to have 3 bowls that we can start working with. We got a jar next to us, and we'll have our spoon. Some folks were curious how we came up with these numbers. These are actually enough that we can fill the jar right to the top. So that's kind of, and it also gave us enough that we could get a decent number of layers or annual layers or varves into our samples. Okay, so how are we going to build these things? You're going to need a volunteer or yourself, and you got your 3 bowls and you got your jar, and you need some patience. So what we're going to start is we'll start with the spring. So we'll take 2½ spoons of sand and layer them in the bottom, sprinkling it around. And then we'll add 2 spoons of our silt and then a spoon of our muddy organic material. And that's 1 year. And so we've got a nice varve there. We got a nice layer there. Maybe rotate the jar as you go. Depends on how careful you want to be. And then if I could borrow from your shampoo bottle, we're going to lather, rinse, repeat. So we're just going to keep repeating this triplet over and over again until we're out of material, and hopefully the jar is just about full if we did our math right. In the past, when I've done this with students, we can get at least 12 years or 12 triplets in here. It really depends on how heaping your spoonfuls are, though. I had a student once got to 20. So if you're the competitive type, you can send me a picture after you're done and we can see how many layers you got in there. And when we are done, we should have a jar that looks like this, and we should be able to see on the sides that we've got our sandy layers and our silty layers and our organic rich layers, and then we repeat them over and over again. And one of the other faculty at CCC, Melinda McKinney, some of you may know her. She's been involved with the Festival of Science a lot. And if you know Melinda, you know she's got a lot of energy. So she helped me out and didn't just send me a picture, but she sent a video, time-lapse video of building her jar. So we're going to run that through quick. Sometimes on Zoom, videos don't stream very well, but I think it still can help you out, and it's not crucial to understanding what we're doing. So let me fire that up. And so again, just repeating those 3 layers over and over again to kind of model our sediments in nature. I had Melinda throw in a few other things because we can do more than just put sediment in. There's other things that land in our lakes. So that's cool. So let's keep moving on. So let's see how we did. So here's an actual picture of a lake core, and you can see that it's got coarser grains and finer grains and really fine grains, and it's got lighter layers and darker layers. So I think our approximation, we did pretty well. Oops. Sorry about that. We did pretty well, so we've got our layers in here as well. So since we've got a good model, we can hold it in our hands and look at it and think about how geologists might do this with a long lake core, which might have hundreds or thousands of layers in it instead of our layers here. So what can we learn from lake cores, and what can we model with our jars now that we've got them built? Well, they're definitely, just like in a tree with counting rings, we could maybe estimate the age of a lake. If I have 500 varves in my core, then my lake might be 500 years old, right? That would be a logical way to think about things. And if I remember back to my college days, I think I remember a lesson where they talked about one of the first ways that folks had an idea of when the last ice age ended was a lake core in Minnesota, I think it was. And they had counted probably a grad student or some other resume building internship type low paying character building task. They got 10,000 annual layers out of that lake. And so if we think about it, if that lake has been here 10,000 years, and we know that glaciers were in that area, that lake wouldn't survive being run over by a glacier, but a lake would form after the glacier leaves. And so we might say that that area of Minnesota was ice-free about 10,000 years ago. And if we did a bunch of lakes all over New York and Michigan and places, maybe we could kind of reconstruct how the glaciers retreated based on how old the lakes are as we head north or south. So that might be something we could put to use and think about things. And so we can get an age of the lake. Sediment isn't the only thing that settles into our lakes. And so we could also have, as anybody in the Flagstaff area, or definitely the Portland area knows now, when we have forest fires, all that ash goes through the air and it does eventually settle down, and some of it falls into lakes and it would settle to the bottom. And so we could have a layer of ash in a lake after a forest fire. And then we might be able to count our way back down to layers of ash to figure out how long ago a fire was or how frequently a fire was. We've got other things that get into our lakes as well. Those of you that have allergies know that pollen gets everywhere. And so just as it can get into your house and settle down, we can imagine that pollen would land in a lake and then slowly settle to the bottom, especially in winter when things get really quiet in the lake when it freezes over. And so our lake is a record of all the pollen that's accumulated over time. And that might tell us about different trees living around. And we also have volcanic eruptions that put ash in the air that falls into different landscapes and could settle to the bottom. So we'll model each of those as we work our way through. So we'll blend a little real science with a little pantry modeling, I guess you could say. So under a microscope, we can actually see the difference between ash from fires and ash from volcanoes. And so this is actually ponderosa pine ash, but you can see it still looks fibrous and woody. This is looking through a normal microscope where you shine light up through your sample. And this is a scanning electron microscope, much more fine grained, but we can still see that patterns in there. So it looks a lot different than pieces of rock that most of the sand and silt would be made out of. So we should be able to, if we're willing to take our time and work with a microscope of a sample from a layer, we should be able to see if there's ash and maybe how much of it there is and things like that. So got some helpers here. Gina and Laurel helped me out and they made a core, and I asked them to throw in some ash. And so we decided chocolate chips would make good ash. So if you think about a jar, if we had a layer of chocolate chips and then we had back to our layers and then we had another layer of chocolate chips, we might interpret this as 2 fires. And if we could count the layers in between, we could even talk about how often this area gets fires. And in the core of a nearby lake, we could do a lot longer record than our jars, but we could get an idea of how often we have fires, maybe try and estimate the thickness of the ash to how bad the fire was. So maybe not just how often do we have fires, but what we often call recurrence interval, how often do we get fires of that magnitude? So that's one way we could model things and imagine what folks could read out of the lake core. We talked about pollen falling into lakes, and most of us just think of pollen as something that makes us sneeze and our eyes water. But if we actually look under a microscope, pollen is absolutely beautiful stuff, and it's all different. And so it actually turns out that you can identify a tree based on the shape of its pollen, or any vegetation. So just like we could pick up leaves and identify trees based on the shape of their leaves, we can identify the vegetation based on the shape of the pollen. And some of it has kind of a buckyball shape, other ones have 3-fold symmetry, other one has 2-fold symmetry, kind of reminds us of Mickey Mouse. And so the folks that study pollen have a database of pictures. And so if we were to sample a lake, we would say, hey, I see 5 different types of pollen, and match up the pictures and say, this is a pollen from this type of tree, and this is a pollen from that type of tree. And if we were 500 layers down, we would be looking at what the forest looked like 500 years ago, the types of pollen that were landing in the lake core. So we didn't want to sprinkle pollen all over your house, so we tried to come up with something else that would work. And so I had some helpers here. Melinda, Maud, and Colleen helped me out. And so I gave each one of them a slightly different pollen record. And for that, we used M&Ms. So either the little tiny ones or the big ones. And so we thought those were really good ways of visually thinking that the pollen is changing because the color of the M&M is changing. What we ran into is one of the biggest challenges of trying to get the M&Ms near the edge of the jar so we could see them. So we actually had 3 jars that we modeled as being a really long core. And so kind of 3 sections of the core. And so if we stacked them together, if it was a really long core, we kind of modeled that blue and yellow M&Ms might represent the pollen from birch and maple trees. And green and orange M&Ms would be loblolly pines and palm trees, palmettos. And then our red M&Ms would be from bald cypress. And so if we think about how we would interpret this, one thing we can see for sure from the bottom of the core to the top, there's been a change in the types of pollen and therefore a change in the types of trees growing in the forest nearby. And if you've seen these trees before, some of you have, some of you haven't, we can think about where they live today. And if we know where they live today, that can tell us the kind of temperatures and moisture conditions they do well in. So our birch and maples, let's tunnel vision on maple, think maple syrup, right? And so birch and maple do well in Michigan and Ontario and New York and Vermont, New Hampshire. So we might picture the bottom of this lake, the oldest part of the lake, it remembers a forest that was similar to these northern forests around the Great Lakes. And then the middle years of this lake's life, most of it remembers loblolly pines and palmetto trees, which kind of is the coastal Carolinas. That's where we see a lot of those today. And then we kind of go into bald cypress trees, and we find bald cypress today in the swamps of Florida and Georgia. Maybe you've heard of the Okefenokee Swamp. So this is a tree that does really well there. So oldest on the bottom, youngest on the top. And so what we've got is a lake that went on spring break, right? It left home in Michigan and drove to Florida for spring break. Okay, that's kind of ridiculous. But it does tell us that this lake changed, the environment changed around the lake. And so maybe we can picture that originally we had a climate like this, and then sometime later we had a climate like this, and then later on we had a climate like this. And so this would tell us that through the life of this long lake, it got warmer and it got wetter. We started in kind of a Michigan, New York, Ontario forest type environment, ended up in a Florida, Georgia swamp environment. So we're kind of goofing around a little bit, but it still demonstrates what we can see in lake cores. And actually, if we think about this a little bit, if this lake had been around a long, long time, during the last ice age, when Michigan and New York were under 5,000 feet of ice, we might expect all the vegetation patterns to have been pushed south of where they are today. So maybe we could have actually had kind of those trees growing in Georgia. And then over time, as the glaciers retreated and things warmed up, those birch and maple forests migrated north and got replaced with other trees. So hopefully that helps as an analogy to see what folks can do. But if we can pull out pollen and we can see a change in the trees, we can start asking questions like, why did the forest change around this lake? One of the challenges sometimes when we focus on climate change is we get tunnel vision on temperature change, but it can also be about moisture changes. We also see areas fill in with sediment and dry up. So some of our lakes over time will often fill up with sediment and eventually dry out. It's just their natural progression. So this jar would be, maybe we start with a bald cypress and replace it with palm trees and eventually grasses. And so this might tell us about a swamp that dried out. We started with a lot of water for the bald cypress, and then later on we had palm trees, like it a little bit drier and sandier, and then a bunch of grasslands. So this we might think about as kind of modeling an environment that dried out over time. Then so we had some more helpers here. Professor Tom Lehman and Dr. Hammy helped us out, and we gave them a really challenging jar to do. So we've got spruce trees on the bottom, and then a layer of forest fire ash, and then we've got some wildflowers and grasses, and then we've got some berries, and then we've got some aspen and poplar trees. And this one is kind of typical what we see up in Alaska and places like that. After a really bad fire, the pollen shows us how the forest recovers. So our oldest layer, again, is on the bottom. So we had a nice spruce forest that was doing well, and then we had a really bad fire. And so after the fire, we wouldn't have seen pollen from the spruce trees. We would have seen pollen from the things that started to grow after the fire. And we often do see wildflowers and grasses take over the area first. And then 5, 10, 15 years later, the berries start to come in. We see a lot of raspberries and blackberries. They love disturbed ground. So they like to come in. And then we get some shrubs and things like that. And eventually we start to see some trees coming in, and it is often aspen and poplar and birch. And if we let this keep going, we might expect the lake would eventually, we'd get some spruce trees coming back into the area. So we might call this is the succession of the forest and how it recovers after a fire. And because of the annual layers in our core, we can actually start to count how long does it take for each stage of recovery after a fire to happen. How many years or decades are we looking at before the aspen and poplar show up? We also have lots of other ash that makes its way into our lakes, and that can be volcanic ash. And if we look at that under a microscope, under a normal transmitted light microscope, we do often look like shards of glass. Under a scanning electron microscope, they look like broken pieces of rock and broken glass. And that's essentially what they are. So again, it looks a lot different than our fibrous ash from our trees. So if we're coring a lake, we could maybe tell which layers of ash are from a fire and which ones are from a volcano. Oops. And so we have another helper. Sandy helped us out with this one. And so she made us a jar. And what we did instead, we wanted to model some volcanic ash. Probably don't want to throw a bunch of rock bits into this, so we decided to stick with the pantry. And so we went with some chocolate chips, and then later on some peanuts or walnuts. And the reason for the difference there is every time a volcano goes off and sends out ash, there's some differences in the chemistry, especially in the trace element side of things, things in titanium and manganese and things like that. So the folks that study the volcanoes, if they're studying a volcano and it's gone off 10 times, they know the chemical signature of each eruption that they've studied near the volcano. And so that means that if we're at a lake, maybe 50, 100 miles away, we can actually talk to them and figure out which volcanic eruption we're looking at because it's got a chemical fingerprint to it. Or these could be 2 eruptions from the same volcano, but again, the chemistry changed a little bit in between. And again, we've got our annual layers, so maybe we can start getting an idea of how often this volcano goes off. And so that might help us out. Nobody remembers the last eruption. And we do see that, again, that ash makes a big impact on folks. We saw that in Europe a couple of years ago when we had the Iceland volcano that I will not try and pronounce when it went off. Here's a map that was produced after the Mount St. Helens eruption, and so we actually had detectable ash over all these states. And so what we might be able to do is use this a couple ways. We could go to some lakes in this area and core them, and if we count our way down and hit the ash layer, it's a way of double checking our counting technique because we know exactly when Mount St. Helens went off. And so we should be able to count down to 1980 and double check our counting and our understanding of how this works. The other thing we might be able to do, say we're looking at an eruption from the volcano that was hundreds of years ago and nobody has a map from that time. Maybe by looking at the lakes, we can see how far the ash spread and maybe which direction it spread. And the geologist could maybe reconstruct how big the eruption was or which way the winds were blowing at that time. Another place that folks do a lot of coring of lakes is Alaska. And so if we're in the Anchorage area, it's got active volcanoes all over the place and very well studied by the Volcano Observatory, Alaska Volcano Observatory. And so it's a similar thing there. If we were to core a lake in an area, we'd see a bunch of ash layers and we can check their chemistries and tie them back to which volcano, maybe even which eruption. And we might even be able to do something like compare one lake to one on the other side, one on this side, and then we can maybe reconstruct which way the winds were blowing and kind of do some analysis of how wind patterns have changed in the area. So there's a lot folks can do with this if they take the time to tease out these microscopic pieces of evidence and if they take the time to count all these layers. So hopefully that's all making sense. Definitely we miss interacting with you and I can't see all the faces and whether you're nodding or you're confused. I'm hoping for the nodding and the thumbs up. That's what we'd like to see. And so again, I want to thank all my helpers who made all these different scenarios and they all wanted to be involved because we miss having you on campus. So it was at least a little way that we could all do this as a group exercise and reach out to you folks in the public. So you see how excited they were. And so obviously they had a great time. And we all know that science is its own reward, but you might be wondering, what am I going to do with the jar now? Well, now you're going to add some more ingredients and you're going to make some brownies. So you have a good experience. And so we'll leave this up there. This is the end of the talk. And so I'll talk some more with Josh, or folks can send in some messages and questions as they go. And so here's some of the ingredients that you're going to need to add. And then you can make some brownies. And if you want to do one of the other scenarios I put on the slideshow, I think this will be, you can watch this again at a future date. And you can do more science or justify your brownie habit if that's what you want to do. And we'd love to see your finished jars. So send us some pictures and you can either put a hashtag on your pictures on social media or you can send me some pictures and I'd love to see them and hopefully you have a good time with this. And if there's any teachers out there that would like a little more detailed about how we put this together for lesson plans or things like that, definitely feel free to send me an email and we'll get back to you as soon as we can. So I'll leave this up for you so you can write all this down and I'll check back in with Josh.
Thanks very much, Kurt. We appreciate you coming out to give that talk. We do have a couple questions filtering in. Todd from Flagstaff asks, does the process of retrieving a core disrupt the sediment layers? And if so, how do you prepare a core before observing it in a lab?
There's always the danger when you pull any core out, whether it's a drill rig for rock or a core, that you lose some of it that goes down. And you know, I haven't been around the actual preparation of this. I've had this as class exercises, but I've never actually, and I've looked for the pollen grains, but I've never been the one that actually did the prep work. So I'm not really sure how they would preserve it. I imagine you want it to dry out a little bit, but you don't want it to, it's a wet, sloppy thing, so you have to be careful. So I'm honestly not sure how folks do that. I know there's some folks at NAU that do a lot of lake coring, and so they might be able to help folks out with the nitty-gritty of how that's done.
And Hector from Mesa asks, what makes the different sediments different colors?
That can be a couple different things. It could be different source areas. And so if we're moving material in from, if we have a stream that's coming in from a little further away, it might be sampling a different bedrock than might be right near the shore of the lake that the waves are breaking up. So it could just be showing us different source regions for the different sediments. And then a lot of it is how much organic material we've got mixed in that layer that makes things darker.
Great. So Sue from Williams asks, can I core sample my jar?
You can take a straw, and actually I find it really helpful at weddings. If you're trying to figure out what the wedding cake is made out of, a little straw down, and you can pull it out and you can go, oh, am I looking at some red velvet or just some chocolate cake? And it might help you make some decisions that way. You can probably do your jar. You might want to put your thumb over the top to pull it out to give it a little bit of suction. I haven't tried that though. I have to put that on my to-do list.
So I'm curious, when you're actually going out to sample, is it difficult to find a good area, or is it pretty universal across the bottom of the lake? Do you have to look pretty hard for a good spot to core?
I think so. Like I said, I haven't done a lot of coring. I remember doing these models like this, and I thought it'd be a fun way to kind of do something with the families. But definitely, if you had a lake, if you're closer to where a stream dumps in, that's going to give you a much different record than across the lake where there's less sediment coming in. And so they do often core several places in the lake. And that's where those layers of ash and thing are really helpful, because you can feel comfortable saying that you're in the same area as far as time goes. I know the friends of mine that did coring in Alaska, they often waited till the winter so they could walk out onto the ice and just use an ice auger. And it was a lot easier than trying to balance on a boat. But most folks, if I remember, there's the folks that did these studies, they were often coring a few places in the lake to see if they were either missing out on some sediment coming in from the stream, or if we get too far offshore, we might be so far out that even the waves can't get the sand out there, and then we might lose some of that resolution. So there is definitely a sweet spot if you want to feel confident that you're counting nicely.
And with these kinds of records, do you see, so within a specific area or from lake to lake in a region, is there a high level of synchronicity that you'll see?
Yeah, it kind of depends on the area and depends on the fire history, but normally we do. Sometimes you see a different chemistry signature to some of these. So like I know folks that worked in the Adirondacks, especially during the acid rain days, depending on the bedrock, we had some lakes that were just perfectly fine and had tons of organic activity and fish and things, and we had other lakes that were so acidic nothing lived in them. So the record of what was settling to the bottom would have been very different during those decades that we had the acid rain problem. And that really came down to the bedrock. If your lake was surrounded by limestone, the acid rain was neutralized. If your lake was surrounded by, say, a slate or something like that, then it was an acidic lake. So sometimes the chemistry comes into play. I think I remember reading that they had cored Watson Lake down in Prescott, and one of the things they could see in the core was that initially the lake got a lot of material from the streams coming in, and then over time, as it kind of sat there, the chemistry of it changed, and therefore the organic material settling to the bottom. Sometimes folks can pull out diatoms, so tiny little microscopic organisms, and so they can see if there's a change in the diatoms. It might tell them about a water chemistry change or a water temperature change over time.
Very cool. Well, I'd like to just say thanks again very much for coming and sharing with us. There's a few more events we'd like folks to participate in today. Just go check out our website, scifest2020.org. Coming up next, we have Can We Control the Weather by our own Brian Klimowski. And then later on this evening, Old Caves Crater Pueblo virtual hike. There's all kinds of fun stuff on there. So thank you again, Kurt Yuengling, for coming out, and everybody watching out there on the interwebs, please show up and participate as you can.
Thanks everybody.